Welcome to a new session. So in our last session we explained how to represent a graph using adjacency list, and then we perform BFS and DFS on an adjacency list. So in this session, first we will represent a graph using a matrix, and then perform BFS and DFS on that matrix to traverse this graph. So let's create another class. So our last class was graph list. It is graph matrix. Graph matrix. Okay. So first, let's create a matrix like this. Matrix. Actually, that should be an integer. Integer. It is a two-dimensional array. Matrix equals a new init. So actually we need to pass the size when we create the object of this graph in the constructor. So let's create the constructor graph matrix. So it should get the size, and that should be like n. Okay. Integer init n. So now we can say matrix equals new init n times n. So we created the matrix, but right now it is an empty matrix. So let's create a method to fill this matrix. That means to add the edges. So public void add edge. So every time we need to pass the both ends of an edge. For example, 1 and 5, 1 and 2, 2 and 5, something like that. So init u and init v. Okay, so as soon as you create the object, you have this empty list there, and now when you add the edges, for example, you have a list like this, but all of them are 0. So now when you pass, for example, uv, you pass 1 and 2, so that means your matrix of u and v equals 1. So same thing if, for example, 1 has a relation to 2, 2 has a relation to 1. So you say matrix v to u also equals 1. So this way you add all the edges into the matrix and you fill your matrix until it becomes like this. However, keep one note here. Let me write a note here. Note. N equals graph size plus 1. Why? So for example, here when you add 1 and 2, matrix is an array. You see that a two-dimensional array. An array is 0-based indexed. That means if you pass 1 and 2 here, 1 and 2, so 1 and 2, for example, here row 1, so it is row 0, it is row 1, but we mean this one. So for that reason we need to create one size larger so that we ignore the index 0. And when we say matrix, for example, let's say 1 has a relation to 2, something like this, it should point here. For example, 1, so suppose there is already index 0 and the index 1 is here. Index 1, row 1, column 2, row 1, column 2, this one. It should point to this one, and we make this part 1. For that reason, make the n plus 1. So now that you know how to add edges into the matrix, now you have a matrix, and now you need to traverse that graph because that matrix represents a graph. And you have two approaches, one is BFS and one is DFS. So once let's do the BFS, public void BFS, public void BFS. So we start from an index and it start from a root. So based on our previous explanations, we already know that when we use BFS, we should have a queue. I already created a queue, and in order to keep track of the visited nodes, we should have another list of visited nodes in order to keep track of visited nodes and to do not visit them again and again. So we need to create our visited list. So as far as it is an array, so for example, you say you check this index, you check this index, and you check the indexes. So it is not like list, like for example, to create a list and then check if there is, for example, number 3 is in the list or not. But here they are all index. So it is easier to make it a Boolean array, and if they are connected, if they are visited, make it true. If not visited, make it false. So you can say Boolean of visited equals new Boolean. So this array should be of size our graph, our n graph size. Graph size, but we don't have a graph size, so let me create that here. Init graph size. So I initialize that here. Graph size equals n. Okay, so we created our visited list also. For example, here we have 6 elements, so the size of this should be 7. Let me check. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that should be 7. We leave the first one empty. So now we have created our visited list also, and we need to create the queue also. Let's create the queue of our type is integer queue equals, and to implement the queue interface, the best option is to implement linked list class, new linked list, because it is easy to get the front element and add new element at the end. Okay, import these classes from java.util, import java.util. Okay, so now that we have created our queue and visited list, so when we call this method, for example, let's start from number 1. So number 1, let's say, so that should be in the first row, and when we give number 1, so we directly add that to our visited and queue also. So let's add that to the visited start. For example, this index is given, the index 0, because the number 1 represents this one. So the index 0 is added to the visited list. So instead of true and false, I write number 1 and 0. That's easier. Okay, so I added to the visited list, and now I add this to the queue also. Queue dot add start. So that means I add number 1 to the queue also. Okay. See, now it helps us here. If our index was started from 0 and the size was exactly to the number of our graph, so this one, it shows the second element in the array. But right now we are ignoring the 0 index. Let's suppose there is the 0, and when we say 1, it directly show this first index. So I added to the queue also, and now let's check the queue. As far as there is something in the queue, we have to keep checking our graph. So we say while the queue is not empty, keep checking the graph and remove the front element from the queue, which is number 1 right now. Take it out and say init node equals queue dot pull. Okay, and when you get that from the queue, now you process that, but right now here we only print that system.out.print node and make a space between them, something like this. Okay, it is node. So you process that number 1, and then you check all its neighbors. By all its neighbors, it means you check every column here, and once you check every column here, that means you have checked the relationship of this node with the whole rest of the node in the list. For example, if you check this one, it represents number 1. So if you check number 1 here with number 2, here with number 3, here with number 4, here with the number 5, and here with number 6. This way you need to have a for loop to walk through all of them. So you say for init I equals 1, so you start from 1, not 0. This way you ignore the index 0. So init 1, and as far as I is less than or equal to the graph size. Oh, good. So I used graph size here, and I can use that here also. And I++. So every time you check if in the matrix, right now you have node, and node is this index in this array, node, and you check all its columns. For example, this one, this one, this one. So you use I, and you say if it equals 1 and is still not in the visited list, we need to add them to the visited. Otherwise, we don't need to check them. And visited is an array. So if it is not added in the array of visited list, for example, we are checking this one. In the matrix, 1 represents this one, this one, and index of I, node and I. So I starts also from 1. So 1 and 1, it is 0, it is not 1, so ignores. Go to the next one. I and 2, so it is 1. And also in the visited, so let me leave the first one empty. I think that makes more sense. Okay. So okay, so 1 and 2, so it equals 1, and it is not visited, it is not added to the visited list also, so we add that to the visited list, number 1 or true. And so first add this to the visited list, visited, the I equals true, and also add this to the queue, number 2, queue dot add I is number 2 at this time. So we added number 2 in the queue. Okay, so we keep processing. At this time, still row is 1, column 3, I3, it is not 1, but I5, I4 also not 1, but I5, it equals 1, and it is not visited, in the visited also. So we add that to the visited list, visited I. So I is 5, 0, 1, 2, 3, 4, 5, this one, 1. So that we added this to the visited list, and also we add this to the queue. So add number 5 to the queue. Okay, added number 5 to the queue also, and so it keeps going ahead. Still no the 1 and I. So 5 check, number 6 it is 0, so we do not check that. So now again it checks while the queue is not empty. Of course the queue is not empty, so we remove the first one from the list and we process that, and now we check all the neighbors of number 2. So that means we check this one. So number 2, again at this time matrix node, this node is 2, and we start from index 0, from the index 1 until the last one. So here matrix node is 2, node is 2. From here we start from here, 2 and 1. So 2 and 1, they have a relation, it equals 1. We see 2 and 1, it is 1. And is it in the visited list or not? So check visited 2. I is 2 at this time. No, I is 1. So you see it is already visited in the already added in the list. So we ignore that. We go to the next one. So 2 and 2, 0, 2 and 3. So at this time visited 3. Is it added in the visited list or not? So visited 3. So 1, 2, 3. It is not yet added here. So we add this here, add that here, and also we add that to the queue, number 3. Okay. So it keep checking ahead. So number 4 is 0, number 5 is 1, 2 and 5. And now check, is already visited or not? Index 5. So 1, 2, 3, 4, 5 is already visited. So we pass that. And number 6, it is 0. So right now it is 5 and 3. So we keep checking until the queue becomes empty. I hope it was clear enough. And now let's check how we can do the same thing using DFS, depth first search. So let me write a separate method. Public void BFS init start. So in the DFS I said we should have a stack and we explore as deep as possible. Let's see how that happens. Okay, so again I will use this visited list and I will use this stack. So I need to create them. So boolean visited equals new boolean g size. Okay, and now create the stack also. A stack integer stack equals new stack. Okay, and add the first node to the stack. Stack dot push start. Okay, so I add number 1 here. Okay, again we start from the first node. So when I add this to the stack, again I have to check if check the graph until the stack becomes empty. So I'm making a while loop. While the stack is not empty, the stack is not empty. Keep checking them, and every time check if it is not visited, check it itself and its neighbors. But if it is already visited, then ignore this. So we say if visited, there's I did not pull that yet. So first remove that from the top element from the stack, and it in node equals stack dot pop. So now you say if it is not in the visited list, if it is not in the visited list, add this to the visited list. Visited the node equals true. Visited node is number 1. So okay, index 1 0 1, that is added here. And now we process that. By process, right now here we only print that. System.out.print node. Okay, so now when here we say pop, we remove that actually, so that should be removed from here. So now we check all the neighbors of number 1, but as deep as possible. So we need to have a for loop. Init I equals let's start from the last one. equals to G size until I is greater than or equal to 1 and I minus minus. Okay, so now for example here the node 1 was given as a start. That means this index was given, so this was given, and now we need to check like this, either go to 5, 4, 6 or like 2, 3. So let's say if matrix C node and I equals 1, and also it is not yet in the visited list, so we add them to the stack. The stack dot push I. So here node is 1 that we removed from here. It is 1, and this I, so node 1, that means that is here, and I is 7, I is 6, I is 6, so we say node 1 and I is the last element, so I mean I should be the last one, like we are not saying that if it is 6 or 7 or whatever, it should be the last one. So here we have 6 elements. Our matrix is of 7 times 7, so this one, this index shows the last index, the G size shows the last one. So and the last one is this one. So in the matrix node 1 column 6, so is it equals to 1? No, it is not equals to 1, so we ignore that, and so we keep moving forward. So we check this one. Now we are here, column 1, row 1, column 5. Is it 1? Yes, it is 1. And is it in the visited list? No, it is not in the visited list. Number 5 is not in the visited list. So we add this to the stack. Add that to the stack. Number 5. Okay, 5 added to the stack. And we keep going ahead. So still node is row 1 and column 5 checked, 4, 0, 3, 0, column 2. So it is 0. And is it in the visited list? No, it is not in the visited list. So push this to the stack also. Okay, 2 also added to the stack. So, and at the end, node 1, row 1, column 1, row 1, column 1, it is 0. So it is not 1, we pass that. So again, the while loop continues. We pop the last inserted node, which is number 2. And when we remove that, we check if that number 2 is in the visited list or not. If it is not, so we add this to the visited list. So come to number 2, add this to the visited list, and check the neighbors of number 2 now. So number 2, this one. So number 2, that means row 2. So we have to check all the columns, that means all the neighbors. So for I equals to the size of the column, which is 7, until it is greater than or equal to I, not I1. I don't know why I made that mistake. So, and at this point the node, it is 2. So we start from I, that means, so from here, row 2, column, last column. So is it equal to 0? No. So we keep going ahead. At this time, column 5, row 2, column 5, is it equals to 1? Yeah, it is equal to 1. And is it in the visited list? Visited list, yes it is. No, it is not in the visited list also. So we add number 5 again to the stack. So remember that in the stack it happens that you can you can add repeatedly, but you cannot visit that repeatedly. If you remember, the same thing happened when we were doing the list. In the stack you can have repeatedly added, but when you're visiting them, if it is already visited, if it is already processed, you don't process again. So again, so we keep going ahead. Row 2, so column 5, it was checked, and we come to column 4, it is 0, column 3, 1. Is it already visited? No, it is not visited. So we add this to the stack also. 3. Okay, so again, row 2, column 3, column 2, and column 1. But column 1, it is already in the visited list. So if it is already in the visited list, we pass that. So we keep going ahead, and this time number 3. So we remove number 3. So now the process is the same. You process until the last element. I hope it was clear enough. And if any part was unclear, you can ask them in the comment sections. I will come to your questions and I will explain them. I know it was quite lengthy and it might be difficult at the first, but it is not that difficult as it looks. If you practice once yourself, you will learn everything. Until the next session, have a nice time, everyone.